Okay, so just briefly I'll introduce what is called the transpose of a matrix. So if you have an n by m matrix, which I'll call A, the transpose of the matrix A is another matrix. It's called the transpose matrix, and it is an m by n matrix. And it's denoted by AT, written as a power, but it doesn't mean a power, it's just a notation, and whose entries are defined by this condition here. So remember this notation. This means this is the entry in the this is the thing in the ith row and the jth column. So the thing that's in the ith row and the jth column of the transpose is equal to the thing that's in the jth row and the ith column of the original matrix. So this is just a formal definition, but informally, the transpose is the matrix obtained by just swapping the rows and the columns of the matrix. So this is a definition. This is a definition of the transpose of the matrix A. So that may seem kind of confusing, but it just takes like one example for you to get the feel for it. So if A is the matrix 1, 2, 3, 4, 5, 6, then the transpose matrix is you just swap the role of the rows and the columns. So matrix A here is a 2 by 3 matrix. The transpose will be a 3 by 2 matrix. And so the first row of A, so this is the first row of A, this becomes the first column of the transpose. So the first column of the transpose is that 1, 2, 3. And the second row of A becomes the second column of the transpose. And that's it. So all you're doing is you're sort of like rotating the matrix. You're not just rotating it because of the way we order the entries of the matrix. It's kind of counterintuitive. But so that's all you're doing. You're just, what was originally a row in the matrix turns into a column in the transpose. That's it. That's all the definition of a transpose of a matrix is. Let's do another example. So there's one example. There's another example. If A is the matrix 1, 2, 3, then the transpose matrix is the column matrix 1, 2, 3. If the matrix is 1, 2, 3, 5, 7, 8, let's keep going, 4, 7, 0. So this is a square matrix. So the transpose will also be a square matrix, but now you're swapping the role of the rows and columns. So and the way I do it in my brain when I'm writing these out is I first read the row, I take the row of A, and then I just write down the column of the transpose. So when I'm writing down the transpose, I always fill in the columns first. So that's all that the transpose of a matrix is. So you're just swapping the role of the rows and the columns. So that is the definition of transpose of a matrix. Okay, so if it's a 3 by 2 matrix, then the transpose becomes a 2 by 3 matrix. The rows and the columns swap, and so the dimension of the matrix swaps as well. Now, I'll just give you a few properties of the transpose. So properties of this transpose, you can think of it as an operation from all types of matrices to all types of matrices. It changes the type of a matrix, as I've mentioned before, because it changes the dimension. But if you just imagine all possible matrices, we don't care if they have different dimensions, then the transpose takes a certain matrix and turns it into a different type of matrix. So you can think of it as a function of the space of all matrices if you want. So what are some properties of this? Well, the first property is that if you take a matrix and you take the transpose, that's a new matrix, and then you can take the transpose again, you get back the original matrix. And that should be obvious. Let's just, so example is you just swap back. So 1, 2, 3, 4, 5, 6. If this is the matrix A, then the transpose matrix is you just swap the rows and the columns. So you get 1, 2, 3, 4, 5, 6. And then if you transpose this matrix here, that would be transposed of the transpose. You're just getting back to where you started. So of course these are the same. So this should be kind of an obvious property, that if you transpose and transpose, you just get back to where you started. So if you swap and then swap back. That's the first property. Second property is that it behaves well with respect to addition of matrices. So if you have two matrices, and assuming they have the same dimension, so for example, they can both be m by n matrices, then we can add them. We can take the transpose of that, and that is just the summation of the transposes of the respective matrices. And again, these properties are all kind of obvious, so you can just sort of see how they work. So if you take the matrix 1, 2, 3, 4, and take its transpose and add that to the matrix 1, 2, 2, minus 1, take its transpose. So you can either so the way I wrote it, you would first take the transpose, so this becomes 1, 3, 2, 4, and this becomes 1, 2, 2 minus 1. That was a bad example because it's symmetric. And then you add them, and so when you add them, you get 2, 5, 4, 3. And that's the same thing as if you first added the matrices. So if you add them, you get a matrix, and then take the transpose. So if you first add them, then you get 2, 4, 5, 3, and then you take the transpose, and of course when you take the transpose, you see that you get the same thing. So it behaves well with respect to addition. And similarly, the exact same. So maybe I'll just write this as like a 2 prime. It behaves well with respect to subtraction. That just follows immediately from addition. Sorry. So it behaves well with respect to subtraction, addition and subtraction of matrices. If you scale a matrix, so if k is a number, then what you can do is you can scale your matrix. You can take a matrix A, and then you can scale it. That just means you multiply all the entries by k, and then you can take the transpose of that, and that's the same thing as just scaling the transpose matrix. Again, all of these are kind of obvious properties. Just do an example of that. So if A is the matrix 1, 2, 3, 4, and say k is the number, say 5, then k times A is the matrix 5, 10, 15, 20. And so if you take the transpose of that matrix, you get 5, 15, 10, 20. And of course that's the same thing as pulling out the 5. You get 1, 3, 2, 4, and you'll just notice that this matrix here is the transpose of that matrix here. So in other words, this thing is actually just equal to K times A transpose. So anyways, so it behaves well with respect to all of the matrix operations. And then the last property, which is not as obvious, is how it behaves with respect to matrix multiplication. So if A is a matrix and B is a matrix, and if their dimensions are compatible, we can multiply them. That gives us a new matrix. Then we can take the transpose of that. And this is the tricky one, so this one you really want to just memorize right away. This is actually the product of the transpose matrices, but in reverse. So you have to swap the order of those matrices. So these are the main properties. So these are the four properties of the transpose. The transpose of the transpose just takes you back to where you started. Transpose behaves well with respect to addition and subtraction. It also behaves well with respect to scalar multiplication, and it behaves well with respect to multiplication. You just have to remember that the order gets swapped. This is very important, that the order swaps. And let's do one easy little theorem. So last but not least, here's a little theorem. So if A is invertible, so in particular that means it's square, then the transpose matrix is also invertible. And let's just tell you what that is. So it's invertible, so therefore I can find its inverse. So its inverse is just the same thing as taking the transpose of the inverse of A. Okay, so over here, the claim is that AT is invertible, so this is the inverse of AT, which the theorem claims does exist. But furthermore, we can give an explicit, we can tell you explicitly what that inverse is. It's just given by taking the transpose of the inverse of matrix A. So this is a very valuable formula. So we'll put this in a box here. So this is a nice formula relating inverses and transpose together. And, I mean, we can even prove it. It just follows, the proof basically just comes down from property 4 here. So, proof is very easy. Proof, assume A is invertible. Okay, then we want to, in order for AT to be invertible, we just need to show that AT times AT inverse is the identity, and we need to do it in both directions, but that's okay. And so if we take this as a definition for what the inverse of the transpose should be, then that would be, we want to show that AT times A inverse of T. So that our goal is, that's what we want. Okay. So let me make this a little bit clearer. So the theorem says that this is the same thing as that. So in other words, we need to show that this product here gives us the identity, but then if we use this property 4 over here, it says that if you have the transpose of something times the transpose of something, it's the transpose of the total thing in reverse order. So that is A inverse times A. Then we take the transpose of that, but A inverse times A is, of course, the identity. And the transpose of the identity is the identity. So that proves it. I'll just do a little bubble here. The transpose of an identity matrix is clearly the identity. So if you take like 1, 0, 0, 0, 1, 0, 0, 0, 1. When you transpose that, you certainly get 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's where that comes from. Anyways, so the proof is not too important. What is important is just for you to memorize this in blue here. So the inverse of the transpose is the transpose of the inverse.